You already now know the concept of logistical growth, and we're going to dive into the calculus soon. But one thing you have to get used to is a little bit of the algebra trickery that may or may not be coming your way. And so I'm going to take you through three different examples on how algebra trickery can work its way into here. So with this very first example, I'm given a logistic growth equation. There it is. And you'll notice that it's not in the form that I wish it was in. I wish this was given to me like this because then I would automatically know the population limit. It'd be very useful to have it in that form. So if I'm given an equation like this and I feel like I need that, I can go through this algebra trickery procedure. I notice a common factor of p, and remember, the most commonly overlooked factoring technique in America today, the GCF. So I factor out a p, and some of you are saying, hey, you could have factored out more than that, teach. Yes, but I wanted to do it in 2 steps. Between these coefficients, I have a very weird GCF of 0.4. But if I factor out a second GCF of 0.4, I now, with quite a bit of a little mental arithmetic, I end up with the same differential equation, or the logistic growth rate equation, now in this form. So I can tell you that in this scenario, the population limit was 1,500, and that's the constant of proportionality. Remember that a surefire way to check to see if you factored correctly, and especially with the GCF, is go ahead and distribute this back in. If I distribute that back in, I better get that. If I distribute this back in, I better get the step up above. That's example number 1 of algebra trickery. Here's example number 2. This looks a little bit closer to what I want than our previous example. But if I take a look at this, this is not that. I want just a regular old p to be here. So I'm going to do a little bit of algebra again. There's my first step. And you might see what I've done. To go from here to here, I've factored out a GCF of 3. Remember, you can always check yourself. Distribute that back, and you can find out if you're on track. Well, did that help me? Not really, because I don't have just a plain old p here. But I'm going to stop 1 second and put an asterisk by this. By the way, I've put these 2 things together just for to make it prettier. But I'm putting an asterisk by this because we're going to come back to this. This is actually another famous form of the logistic growth equation. But let's keep on keeping on, because I don't have just a p here. This 1200 in the denominator is annoying me. Well, I can teach him or her. I get rid of that 1200 in the denominator by factoring out a 1 over 1200. So that's another GCF. And if you're skeptical, distribute it back and see if you ended up back there, which you would. And then the final thing is, in this case, that's a little clunky out there, so this and this go together to give me a very small constant of proportionality. But now I know my population limit was 1,200. It wasn't necessarily obvious up there, but I bet some people are going to find some tricks to look at this and know what the population limit would be. I'm not worried about that. Let's look at this, because I said that's kind of famous. I'm going to concentrate on it down here in the purple. And if you remember earlier, we said the growth rate is always some sort of relationship between the population limit and the current population value. Well, this is another way to show that. Here's our constant of proportionality and then our current population. But if I think of this 1 representing 100% of the population limit, and the p over 1200 representing the percent or fraction of that limit that I'm currently at. So if the population was at 800 out of 1200, we're at about a 67% of capacity. So 100% capacity minus 67% capacity, or 67% current level is really the difference between the current population and the eventual limit. So it would be legal for you to be given an equation in this form and still be able to jump to the conclusions that we can when we're given an equation in, say, this form right here. In fact, population limit. You could do a web search of logistic growth, and this may be the form of equation in one search, and this might be the form of equation in another search. All right, we've got one more algebra trickery example to go for. We'll go through this one a little bit quicker. Take a look at this. Hey, that's in that semi-famous form, not the original form we learned, but the other form, 100% of population minus the fraction of the eventual limit that we're currently at. By the way, I'm using y's instead of p's. That's totally legal. I look at this and I would say, hey, that population limit better turn out to be 100 or math is broken. I'm going to unveil all these steps at once, and you can pause it and digest them if you want. But basically, I'm factoring out that pesky 100, and then I've got some issues here that I can just eventually turn into a decimal if I wanted them to be a decimal. So these were 3 different examples of some algebra trickery, and hopefully you become good at turning the equation into something that's more useful to you. And if you do like that form, that's totally fine to use. And you might be wondering, why would you ever get an equation in this form? But if you take a look at that, that's a polynomial that's ready for the power rule. If we were going to be doing some calculus curve sketching on this, this might not be such a bad form to have. See ya.